Picture this. You drop a $20 bill into a savings jar every single week. After 1 week, you have $20. After 2 weeks, 40. After 3 weeks, 60. Those numbers 20, 40, 60, 80 aren't random. They're all multiples of 20. By the end of this video, you'll be able to spot multiples of a number instantly, use quick divisibility tests to check huge numbers in your head, and break any counting number down into its factors. Let's start with the idea of a multiple. A multiple of a number is what you get when you multiply that number by a counting number. That's 1, 2, 3, 4, and so on. So the first 6 multiples of 2 are 2, 4, 6, 8, 10, and 12. And here's something you probably already sensed. Every multiple of 2 ends in 0, 2, 4, 6, or 8. That gives us our very first shortcut. Let's check 489. The last digit is 9. That's not in our list, so 489 is not a multiple of 2. Now look at 3714. Its last digit is 4, which is in our list, so 3714 is a multiple of 2. Notice how we didn't have to divide anything. Multiples of 5 have a similar shortcut. Every multiple of 5 ends in either 5 or 0. And multiples of 10 are even easier. They always end in 0. Now here's where it gets interesting. What about multiples of 3? Let's look at the first few. 3, 6, 9, 12, 15, 18, 21, 24. The last digits are 3, 6, 9, 2, 5, 8, 1, 4. There's no pattern in the last digit at all. But watch what happens when we add up the digits of each multiple. For 12, we get 1 plus 2, which is 3. For 15, 1 plus 5 is 6. For 18, 1 plus 8 is 9. For 21, 2 plus 1 is 3. Every single digit sum is itself a multiple of 3. A number is a multiple of 3 if the sum of its digits is a multiple of 3. Let's try it on a bigger number. Is 645 a multiple of 3? Add the digits. 6 plus 4 plus 5 equals 15. Is 15 a multiple of 3? Yes. So 645 is a multiple of 3. And if we check by dividing, 645 divided by 3 is exactly 215. It works. Try one yourself before I show you. Is 10,519 a multiple of 3? Pause and add up those digits. The digit sum is 1 plus 0 plus 5 plus 1 plus 9, which is 16. Is 16 a multiple of 3? No, 15 is and 18 is, but 16 sits between them. So 10,519 is not a multiple of 3. When a number m is a multiple of n, mathematicians also say m is divisible by n. Same idea, different word. Here's the full toolkit of divisibility tests you should keep in your back pocket. Let's put the whole toolkit to work on 1,290. Divisible by 2? Last digit is 0, yes. Divisible by 3? Digits sum to 1 plus 2 plus 9 plus 0, which is 12, and 12 is a multiple of 3, yes. Divisible by 5? Last digit is 0, yes. Divisible by 10? Last digit is 0, yes. So 1,290 passes all 4 tests. Now let's shift to factors. If 72 equals 8 times 9, we say 8 and 9 are factors of 72. Factors are the numbers you multiply together to build another number. And finding all the factors of a number is called factoring. Here's the systematic way to find every factor of a number. Divide by 1, then 2, then 3, and so on. Whenever the division gives a counting number, both the divisor and the quotient are factors. Stop when the quotient becomes smaller than the divisor. Let's factor 72. Keep going. 72 divided by 5 is an accounting number, so 5 is not a factor. 72 divided by 6 is 12, factor pair 6 and 12. 72 divided by 7 is an accounting number. 72 divided by 8 is 9, factor pair 8 and 9. The next divisor would be 9, but 9 times 8 already appeared. Our quotient would be smaller than our divisor, so we stop. Listing every factor from smallest to largest: 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, and 72. 12 factors in all. Some numbers have lots of factors, like 72. But some numbers have only 2 factors, 1 and themselves. Those are called prime numbers. A number greater than 1 that has more than 2 factors is called composite. To test if a number is prime, try dividing it by each prime: 2, 3, 5, 7, 11, and stop when the quotient is smaller than the divisor. Is 83 prime? Its last digit is 3, so not divisible by 2. The digits sum to 11, which is not a multiple of 3. It doesn't end in 5 or 0. 83 divided by 7 is about 11.86, not a counting number. Now try 11. 83 divided by 11 is about 7.5, and this time the quotient, 7.5, is smaller than the divisor, 11, so we stop. No prime divides 83, so 83 is prime. Compare that with 77. Its last digit isn't in the multiples of 2 list. Its digit sum is 14, which isn't a multiple of 3, and it doesn't end in 5 or 0, but 77 divided by 7 equals exactly 11. Found a factor. So 77 is composite. Look how far you've come. You can spot multiples of 2, 3, 5, 6, and 10 without doing any long division. You can find every factor of a number by walking up from 1. And you can tell prime from composite by testing just a handful of small primes. Next time, once we know a number's factors, can we break it down even further, all the way to a unique fingerprint made only of primes?